We talked about how to do derivatives on your robot in the last video, so let's talk about integration in this video. Just like we said last time, oftentimes we get dynamics and other sorts of important robot concepts in these equations that have integrals and derivatives in them, but computers typically need some sort of discretized form of the equations, and robots in particular get updates at discrete times as they're running. So how do we build these discrete systems that are also real-time capable? In this video we're going to talk about the other half of the equation, the numerical integration. So let's step back a step here. What is an integral? The integral is the sum over all the time steps from some 0 point to some endpoint, which we want to look at the limit to infinity there, where you take the value of the function times the distance traveled on the x-axis to get to the value, and sum it all up, and you get the result, so the integral. But again, robots don't really like to deal with infinities. Just like with differentiation, they don't like to deal with zeros. Here we don't really like to deal with infinities. So how can we get around this problem? The question is then, what if we have finite step sizes? So a finite number of steps, so a finite space between the steps, and the answer is that there are really many different ways to do this. The first and by far simplest method is to just sort of assume that everything that you see is a rectangle. So you're looking at the area under this curve, which is really what we're getting at with integrals, and let's just assume that every single part of this is a rectangle. You can see in the drawing here, sometimes this overestimates, sometimes this underestimates, but we're just looking for an estimate. So what are we looking at then? If we get some update, so our function value f, at some step x, and we multiply that by whatever the delta x is since the last time we got the update, we add all those things up together, we'll get some estimate of the integral. Let's do an example here. Let's say that your robot has a speedometer, but no way to actually measure the distance it's traveled. So how do we then estimate the distance it's traveled? How do we integrate over that? So starting at t0 equals 0, you start in some position, so we'll call it distance 0. You drive for a bit. At t1 of 2 seconds, you get an update. The update says you've been traveling 0.75 meters per second over these last 2 seconds. Now in practice, you're probably not going to be driving exactly 0.75 meters per second over 2 entire seconds, but it's close enough, and in general with robots you get much faster updates, so more like 10 times a second updates rather than once every 2 seconds of an update. So we take this 0.75 meters per second here, we could multiply that by the 2 seconds, and we'll get the distance that we traveled. This assumes we didn't accelerate or decelerate in here, it assumes we had a constant velocity, but again we're just looking for an estimate, we're not looking for an exact number. So we can say, with a fair amount of confidence, that our distance was somewhere close to 1.5 meters, our 0.75 meters per second times our 2 seconds traveled. Robot moves again a little bit. 2 seconds later we get an update, 4 seconds, and it says this time we've been traveling at 0.1 meters per second. So how far did we travel this time? Well, our delta t is 2 seconds, right? Because we went from 2 seconds to 4 seconds, so that's 2 seconds in between. And our v2 is 0.1 meters per second, so we take our v2 times our delta t there, and we'll end up getting d2 of 0.2 meters. So we were going a lot slower that time, we only traveled 0.2 of a meter. And we can add all this up and say that our total distance traveled then is 1.7 meters. So just the two estimates there together. And this is probably good enough for most of the things you'll need in this class. So if we assume everything's a rectangle, we get this equation here. We can again look at the output compared to reality. So if we have an integral of a cosine here in blue compared to the numerical integration in orange, we can see that it's not exact. The numerical integration at some points overestimates, at some points underestimates, or really comes very close to the actual true value. But in general, it's pretty close. So it's probably close enough for the types of things we're going to be doing. But in case it's not, here are two other methods. So on the right-hand side, you'll see a graphical depiction of the trapezoid rule, trapezoid method here, which is where you assume that instead of a rectangle, it's a trapezoid, and one point of the trapezoid is your point on the x-axis where you started, another point is the point on the x-axis where you finished. Your third point there is the point on the function that you were at x1, and then the fourth and final point is the point on the function at x2. So what you do here is you just take the area of the trapezoid, and that is your estimate of the integration over that time. This is really useful if you're end up with sparse updates from your robot, so you don't get updates very often. Maybe in the updates every 2 seconds method, this would be a better strategy, so you could account for any sort of acceleration or deceleration in there, but it's still an approximation. You'll see it doesn't quite estimate the area under the curve quite right over there. A better but more complex method is the Runge-Kutta method on the left here. And this one will actually take 4 different values. It'll take the starting point and the ending point, and then it'll take 2 other estimates that sort of underestimate and overestimate where it should be, depending on what the curve looks like. And it'll take a weighted average of that, which you can see on the equation at the left. And that can give you a fairly accurate estimate of where you actually are. It's used often in computational physics, but it's probably not needed, especially for this class where we're just doing some fairly simple equations. So in summary, in practice, our updates tend to happen pretty quickly. On the DuckyBot, most updates will be about every 1/10 of a second or so. So that's fast enough that we don't really need to care about acceleration, deceleration, that sort of thing, because it's not going to be that much of a difference over a 1/10 of a second. So we tend to use the rectangular method, or maybe the trapezoidal method if you really want to. You can improve the rectangular method a bit by taking the average between your 2 function points and using that as your height of the rectangle. But this is probably not really necessary in this class. So unless you have sparse updates or need a lot of extra precision, you can use the rectangular method. If you do, you may want to use the trapezoid or Runge-Kutta method.